This is Introduction to Biostatistics using R. We're in Chapter 2, Descriptive Statistics. This is Part 3, and we're looking at grouping a continuous variable. And what we did before was we tabled variables that were discrete, had specific values. But here, if our data is, say, age, how do we group it and then summarize it in a table or even draw a picture of it? We have to create these class intervals for it, which is a grouping. So I really think that you need to think hard about this. And the groupings need to be clinically meaningful relative to the disease that you're studying. So if you're grouping age, does young, middle-aged, and old make sense? Or maybe every decade or every 20 years. There has to be, and it has to be is a little too strong. I recommend that you have a clinically meaningful way to group your data. But now if you don't, there's dozens of different algorithms that you can use to how many classes, where to separate them. And this is just one of many. So first of all, you need to look at the range of your data, the smallest and the largest, and what's that number, the largest minus the smallest. You have to determine the number of classes. It's recommended 5 to 15, not many more, unless your data set's incredibly large. There's algorithms that you can determine the number of categories, but we're not going to look at that. We're just going to let R do it. But, in this process, the width of your interval is essentially your range divided by the number of categories. You have to be careful about your boundaries. You want to create it with enough precision that not one of your data points can fall on a boundary point. Because if it falls in a boundary point, is it above it or below it? Or where do you assign it? So if your data only has one decimal, then your boundaries should have two decimals in it. So your data can't fall on a boundary. You can just count the number of observations in each group, and then we can create a table. And in a few pages down, we're going to look at a histogram, which is a way to plot these data. Now, in many cases, right, well, frequencies is probably should always be done, right? Because that's in a demographic table or a summary table of your data. You want to know how many observations fall into each. But what's also nice is what's called a relative frequency, and then that's the fraction or the percentage of data that fall into each of those categories. So if you're looking at organ transplantation, specifically kidney transplantation, and 60% of your patients are between 30 and 60, well, then that's a meaningful number, right? And so the as opposed to just a count, then you have to do that mental math in your mind, which that's what calculators are for. So it's often nice to create the relative frequency in there. And in these relative frequencies are estimates of probability. And you'll see, because in any distribution, the area under the curve is probability. So if we can create some sort of picture with these proportions or these relative frequencies, then it's associated with probability. Now, there isn't a range function. So in these calculations, we needed to find the range, which is literally you take the largest minus the smallest value. And there's not a function in R that does that. So if we take a random sample from a normal distribution, sample size 100, when there's no other parameters here, then the mean is 0 and the standard deviation is 1. But there is a range function of our data. And what it does, it outputs the minimum value in our sample and the maximum. So let's store that into a new variable. So remember, it's now a vector of length 2. And I put the parentheses so we can see this assignment happen. So then I take the second element in the vector minus the first element in the vector, and I get the range. Now later, I use something a little, in my mind, a little easier. It's called the diff function. And this diff function is used a lot in time series analysis. So if you're ever lucky enough to take a time series class, you'll become one with that function. So our data set, and so what this does is it creates a vector of length 2, and this just takes the difference from a latter to an earlier value, and you'll get the same thing. So let's look at histograms. Now this histogram is a way to create a graph of a continuous variable that we have put into groups or classes. And a picture's worth 1,000 words. I've created tens of thousands of histograms and plots, and investigators love them, and they're very easy to interpret and understand, and sometimes they're disease specific on how you make the interpretations. But it tells us the center of the data. There's variability associated with the histogram. It helps us detect these outliers that don't follow the normal pattern of the data. And the function is histogram. So we take a random sample from standard normal, and we just simply say histogram, and then this is it. And boom. So we can get some sort of measure of central tendency. There's a variability associated with it. I don't see any outliers. And this is in frequency. This is so there. I'm going to call it 30 observations between there, right? And then there are, what is that? 3 or 4 observations in here. Now, wouldn't it be nice to know what proportion of the data falls in here? And that's that relative frequency that we were talking about. So here we say, let's turn off this frequency count, and then it uses density or the proportion in that category. So it's the same thing, histogram of our data, but we don't want frequency. We want proportions or density. And now this is it. So you can kind of see that 30% of the data fall in here. And we could do that mental calculation in the previous one because we said there were 30 and our sample size was 100. So of course it's 30%, but it's not always that easy. So here there's 17% in this category. I don't know, but it's going to be close. Now histograms are very useful, and you should use them a lot. Sometimes though, people like a smooth curve over the histogram, or just the smooth curve itself. And that's called a frequency polygon. Now, we're not going to create this by scratch. We're going to make use of the histogram function. So it not only creates a plot, which is here, there's so much information stored in that function that we can store it in a variable and then use this variable later. Okay? So create a random sample. Let's create a histogram. We're not going to plot it because it'd be the same plot, but we're going to store all that information that histogram creates into a variable called H. Now, str is a command that I think you should get to know, and it stands for structure. It tells us the structure of an object. So here it says this object H has 1, 2, 3, 4, 5, 6 different variables, and their breaks, counts, density. And so this is the interval in the histogram. And this is another interval, and this is another interval. And then these are the counts that are associated with being in those intervals. Now, instead of counts, we could use the density or the proportion of being in that category. This is the midpoint of the interval. So notice here, that midpoint is 2.75. The midpoint of this is negative 2.25. So we can make use of that. So with this object H, let's plot. And the reason I do this is so I have direct access to those variables. So let's plot midpoint as the X and count as the Y. And let's use both line and points. And so this is what we get. And so we get this, it's like a density function now. And then area under the curve is associated with probability. But maybe I didn't want counts. I wanted the density. Well, within H, that information is there. So let's plot the mids versus density. And both, of course, the shape is the same. It has to be. But the label is different. Now, what if we wanted to plot the histogram and then this frequency polygram on top of it? So we just say histogram X, and since we didn't say plot false, it creates a plot, but also stores everything in H. So now with H, we can create these lines that fit over the top of it. Cool. Now a cousin to the histogram is called a stem and leaf display. And it's a way to organize the data in a histogram-like fashion, but you still get to see your data. So here, like, what are the data values in this group? We know that there's 20 some, but what are they? You don't know that. You can only see the trends or proportions or densities. And a stem and leaf attempts to counteract that. So it's a visual display of organizing the data. So we take a random sample, and then we use the stem function, and it creates this. And so if you tilt your head to the right, it looks like a histogram, right? And you can see that it's very normal-like, as it should be, because we created it. We took a sample from a normal density. But it's not only a histogram, you get to see the actual values. So one of the values is negative 2.3, right? The decimal point is at the dash. So negative 2.2, negative 2.1. This is negative 1.9, negative 1.8. And they're ordered, right? And so you get a feel for the data. Now, I think the stem and leaf display is really only good if you have 100 or less data points. It starts to become a little bit overbearing if you have too much data, and you should really fall back onto the histogram. I like these, but in general, I haven't put them in many reports because the data sets that I have generally worked with are extremely large, and they're just not conducive to the okay, so in the next video, we'll look at measures of central tendency. See you then.